Have you ever wondered why we can fly into space but cannot make a car that won't rust in 10 years? We are accustomed to considering ourselves the pinnacle of technological progress, looking down on our ancestors with arrogant condescension. However, beneath the layers of Earth lie silent testimonies that we have lost something fundamental in our pursuit of speed and profit. The Roman legions used iron that, 2 millennia later, looks as if it came out of the forge yesterday morning. Our bridges and fences, on the other hand, begin to rust before builders even have time to hand over the project to the customer. This seems like an impossible paradox, contradicting all the logic of scientific and chemical development. We call those times the Dark Ages, but their metal survived empires, wars, and history itself. Watch the video to the end, and you will learn how ancient craftsmen, without knowing Mendeleev's periodic table, created an eternal material, the secret of which we are only now beginning to understand. What if I told you that everything you believed about the primitiveness of ancient technologies is not true? In the mid-20th century, archaeologists in Scotland stumbled upon a discovery that literally turned historians' ideas about metallurgy upside down. At the site of the ancient Roman fort of Inchill, which had been suddenly abandoned by the Legion, researchers discovered a giant pit. This cache was several meters deep and filled to the brim with rusty earth and strange objects. When experts began to clear it layer by layer, they realized that this was not just a garbage pit. It was the Empire's strategic reserve, hidden from enemies during the garrison's emergency retreat. The pit contained almost 7 tons of iron nails of various sizes and purposes. According to the laws of physics and chemistry, after almost 2,000 years in the damp Scottish soil, they should have turned into red dust. Moisture, oxygen, and aggressive salts in the soil leave no chance for ordinary iron over such a long period of time. Archaeologists expected to see only shapeless, oxidized lumps that would crumble in their hands at the first touch. However, when they took samples from the center of this huge mass, they were in for a real shock. Under a thin outer crust lay clean, shiny, and completely intact metal. The nails looked as if a Roman blacksmith had forged them just a couple of days ago and simply forgotten to put them away in the warehouse. Even the smallest traces of hammer blows and technological marks were visible on the surface of many of the items. This discovery sparked heated debate in the scientific community and prompted laboratories around the world to request samples for analysis. No one could believe that primitive iron could resist corrosion better than modern alloy steels. It seemed like some kind of hoax or dating error, but the facts were irrefutable. The fortress was abandoned in the 1st century AD, and since then, no one had touched the cache. Scientists conducted hundreds of tests in an attempt to unravel the secret of this incredible material's durability. They cut the nails, etched them with acid, X-rayed them, and studied their structure under powerful microscopes. It turned out that the outer crust, which was initially mistaken for ordinary rust, actually functioned as an airtight cocoon. Inside this cocoon, the metal was preserved, protected from the destructive processes of the external environment. It was like a natural time capsule created by the properties of the material itself. But the most interesting thing was hidden not on the outside, but inside the crystal lattice of the ancient metal. The structure of Roman iron turned out to be fundamentally different from the metal we use in construction today. It was not a homogeneous, dead alloy, but a complex, almost organic composition. It combined various elements that are considered harmful impurities in modern metallurgy. We spend billions of dollars to purify steel of everything unnecessary, achieving perfect purity. The Romans, willingly or unwillingly, used these impurities to create a protective barrier. Each nail from Inchill was an individual product with its own unique chemical passport. Unlike modern stamping, where millions of products are identical to each other like clones, here you could feel the hand of the master. Differences in composition were even observed in different parts of the same nail. The head could be softer and more viscous, while the tip could be hard and elastic. This spoke to the complex manufacturing process that we have lost in the pursuit of mass production. This discovery made us take a fresh look at what we call quality in the modern world. We create things that are designed to last for a warranty period, after which they must be sent to the landfill. The Romans built infrastructure designed to last forever because they could not afford to redo their work. Their economy and military machine required reliability that did not depend on the vagaries of weather or time. And the treasure they found was the best proof that they had achieved their goal. The most striking thing is that these nails could be used for their intended purpose immediately after being extracted from the ground. Imagine, you take an object that has been lying in the mud for 20 centuries and hammer it into a board. It does not bend, does not break, and holds the load just as it did on the day it was created. This demonstrates the superiority of ancient engineering over the modern consumer approach. We have learned to make a lot and cheaply, but we have forgotten how to make things that last for centuries. The story of the nails from Inchill is just the tip of the iceberg in the mystery of Roman iron. Columns, staples, and tools that refuse to rust are scattered all over the world. They stand in the rain, wind, and scorching sun, ignoring the laws of oxidation. Each such artifact is a silent rebuke to our modern industry. And every year we find more and more evidence that the secret lies not in magic, but in technology. Do you agree? Please tell us what you think about this. Did they really know how to do things better in the past, or is this just survivor bias? Every opinion is valuable. Want to know a secret that will change your life and your view of the world around you? To understand the greatness of Roman metal, we must first understand why our modern steel surrenders so catastrophically quickly to nature. We live in a world that is essentially slowly burning in the cold fire of oxidation. Corrosion is the natural tendency of metal to return to its original state, to become ore again. We expend enormous energy to wrest iron from the shackles of oxygen, but nature always takes it back. And in the modern world, it does so at an alarming rate. Modern steel is a product of giant factories, where the main criteria are purity and uniformity of the alloy. We remove almost all impurities from the metal, leaving only iron and carbon. It would seem that pure material should be stronger and more resistant to external influences. But it is precisely this sterile purity that makes it defenseless against aggressive environments. The homogeneous structure allows rust to spread evenly and deeply, encountering no obstacles. When a modern car body gets scratched, a chain reaction is triggered that is almost impossible to stop. Moisture gets onto the exposed metal, an electrochemical process begins, and rust starts to eat away at the coating from the inside. Iron oxide takes up more volume than the metal itself, so it causes the paint to swell and peel off. Rust does not create a protective layer. It is loose and porous, like a sponge. It absorbs even more water, transferring it deeper into the metal that is not yet damaged. This process is similar to a cancerous tumor that eats away at a structure until it turns to dust. We try to combat this by coating steel with zinc, paint, and polymers, but any protection is temporary. As soon as a micro crack appears, the process of destruction starts again. We have become hostages to constant maintenance and replacement of parts. Our economy is built on the idea that things must break so that we buy new ones. Roman iron behaved fundamentally differently when it came into contact with water and air. It did not try to fight nature through perfect cleanliness, but used its internal characteristics for protection. Instead of loose, destructive rust, a dense, dark patina formed on it. This film acted like skin, covering minor damage and stopping oxygen from getting in. It didn't peel off, but became part of the product itself, making it stronger over time. Imagine the difference between a modern glossy facade and an ancient stone wall. The facade requires cleaning and repair, while the stone ages gracefully, covered with moss. So it was with Roman iron. It aged but did not die, retaining its structural integrity. Modern metallurgy, in its pursuit of production volumes, has overlooked this important nuance of interaction with the material. We have created metal that is strong in terms of tensile strength, but weak in terms of durability. The problem also lies in how we produce metal. Huge blast furnaces melt ore into a liquid state, completely destroying its natural structure. We then pour this soup into molds, obtaining a crystal lattice that forms chaotically as it cools. This process does not allow for the fine-tuning of the structure that was available to ancient blacksmiths. We have sacrificed the quality of the material for the sake of quantity. Today's engineers build corrosion allowance into their designs, knowing in advance that some of the metal will disappear. We build bridges thicker than necessary, simply to give them time to decay. This is an admission of defeat to the elements that would have been incomprehensible to a Roman architect. For them, iron was a precious resource, and allowing it to rust was an unaffordable luxury. We call our age the Iron Age, but in reality, we are living in an era of rust. Our landfills are filled with the remains of cars and household appliances that have served for a negligible period of time. This is a colossal waste of the planet's resources, energy, and human labor. And looking at a Roman nail that survived the fall of the greatest empire, we feel a little ashamed of our achievements. But what exactly made Roman iron so special at the microscopic level? Are you ready to find out what trash inside the metal saved it from destruction? I discovered this by accident while studying old metallurgists' reports, and it completely changes the perception of quality. The main secret of Roman durability was what we would today call a defect or dirt. Roman iron, or more accurately, wrought iron, was saturated with slag. These were microscopic fibers of a glassy substance that permeated the entire piece of metal. In modern production, the presence of slag is considered a gross violation of technology, leading to the rejection of the entire batch. For ancient metal, these slag inclusions played the role of reinforcement in concrete. They created a layered, fibrous structure resembling wood rather than a homogeneous piece of metal. If you look at a piece of broken Roman iron, you will see not a granular structure, as in modern steel, but fibers similar to a torn rope. These strands of silicate slag acted as a physical barrier to corrosion. Rust could not pass through them. It hit the glass and stopped. Imagine modern steel as a piece of refined sugar. Once water gets on the edge, it soaks through the whole piece. Roman iron was like a tightly compressed stack of waterproof sheets. Corrosion could damage the top layer of metal, but it immediately hit a layer of chemically inert slag. To reach the next layer of pure iron, rust had to bypass this barrier, which took centuries. It was a natural built-in protection at the micro level. The amount of these slag inclusions could reach several percent of the total mass of the product. It was they that gave ancient iron its unique properties and appearance. The slag actually broke the metal into thousands of fibers isolated from each other. Even if rust ate through one fiber, the neighboring ones remained intact. This ensured the phenomenal durability of the entire structure, even in the presence of external damage. In modern metallurgy, we strive to remove all slag to make steel as ductile and tear-resistant as possible. We have achieved tremendous success in mechanical properties, but we have lost this natural composite protection. Our steel is too clean, too open to external influences. We have removed the metal's immune system, replacing it with external coatings that are easily damaged. The Romans did not add slag on purpose. It was a byproduct of their iron production technology. They did not melt the metal to a liquid state, as we do in blast furnaces. They cooked it in bloomery furnaces, where the iron remained in a solid, dough-like form. The slag simply did not have time to separate completely and remained inside the bloom, which was then forged. It was this flaw in the technology that became its main advantage in the long run. What seemed like an inability to purify the metal turned out to be the creation of a unique composite material. It is reminiscent of modern developments in the field of carbon fiber, only made thousands of years ago from earth and fire. Nature itself suggested the ideal structure for a durable material. These glass threads inside the iron also acted as stress distributors. They dampened vibrations and prevented the formation of large cracks that could split the product. The metal became ductile and fatigue-resistant, which was critical for swords, tools, and construction staples. It could bend, but it was incredibly difficult to break. We often think of progress as a movement from primitive to perfect. But the case of Roman iron shows that sometimes progress discards useful properties for the sake of production convenience. We have learned to smelt thousands of tons of steel per hour, but we have forgotten how to smelt steel that lasts for thousands of years. The raw smelting process was slow and labor-intensive, but it produced masterpieces. If you enjoy learning about these hidden details of history, be sure to like this video. It will help us find even more forgotten secrets of antiquity. Don't forget to subscribe to the channel so you don't miss any new videos. What I am about to show you is prohibited in 12 countries when it comes to modern steel standards. The second key component that ensured the immortality of Roman iron was phosphorus. In modern industry, phosphorus is considered a harmful impurity that causes cold brittleness. The metal becomes fragile in the cold. Engineers do everything possible to reduce the phosphorus content to hundredths of a percent. However, in ancient samples, its concentration sometimes goes off the charts, reaching values that would be considered defective today. The Romans could not effectively remove phosphorus from ore because their furnaces did not provide the necessary temperature and chemical environment. Phosphorus passed into iron from the ore itself, and importantly, from charcoal. But instead of spoiling the metal, this element played an unexpected role in protecting it. High phosphorus content radically changes the corrosion process, turning an enemy into an ally. When phosphorus iron oxidizes, the familiar loose rust does not form on the surface. Instead, a very thin film of iron phosphates forms. This film acts as a natural primer. It is very dense, hard, and firmly bonded to the base metal. It blocks oxygen from reaching the deeper layers, effectively preserving the product. This process is called passivation, and today we try to recreate it artificially using chemical reagents. Roman iron possessed this property naturally, thanks to dirty ore and technology. The longer such an object lay in the ground, the thicker and stronger this phosphate armor became. Over time, the reaction stopped completely, and the metal fell into hibernation for millennia. Interestingly, phosphorus was distributed unevenly in the metal due to the lack of complete melting. Areas of high and low concentration formed, creating a complex pattern on the surface of the etched metal. These zones functioned as microscopic galvanic couples, but ultimately this only contributed to the formation of a more stable protective film. The result was a self-regulating protection system. Scientists have discovered that phosphorus is responsible for the preservation of the famous iron pillar in Delhi, which has not rusted for 600 years. The technology used to make it is very similar to that used by the Romans. This confirms that the ancient world, from Britain to India, knew the secret of phosphorus iron. Even if they didn't understand the chemistry behind it, they empirically chose the ores that produced eternal metal. Modern weather-resistant steels, such as Corten steel, use a similar principle. Alloying elements are added to them to cause controlled rusting and the creation of a protective crust. But the Romans achieved this without sophisticated laboratories, simply using the gifts of nature. Their primitive method turned out to be the forerunner of modern nanotechnology for surface protection. Of course, phosphorus iron had its drawbacks. It was more brittle than modern steel. Roman blacksmiths knew this and used this metal where hardness and durability were important, rather than flexibility in cold weather. They skillfully combined different types of iron, welding them into a single product. This required a deep understanding of the material, which was passed down from generation to generation. Today we remove phosphorus because we need universal steel for everything from paper clips to skyscrapers. We have chosen the path of standardization, sacrificing unique properties for predictability. Roman phosphorus iron was capricious and difficult to work with, but it rewarded hard work with eternal life. It was a material with character, but chemical composition is only half the story. What ancient metallurgists fed their furnaces played a huge role. In the next chapter, you will learn how a change in fuel permanently destroyed the quality of metal. In metallurgy, fuel is not just a source of heat, it is an active participant in the chemical reaction. The Roman Empire ran exclusively on charcoal. The vast forests of Europe were cut down to feed thousands of blast furnaces and forges. Charcoal is a surprisingly clean fuel, with virtually no sulfur or other aggressive impurities. It provided a gentle, clean heat that gently reduced iron from ore. The Industrial Revolution, which gave us the modern world, made a fateful substitution. The forests were depleted, and humanity switched to coal and coke. This made it possible to increase production volumes thousands of times over, but it also brought with it an invisible killer of metal: sulfur. Coal is saturated with sulfur, and during the smelting process, it eagerly enters the structure of steel. Sulfur is a slow-acting poison for iron. Even in microscopic doses, it creates pockets of stress and corrosion in the metal. Sulfide inclusions become the points from which rust begins. In the presence of moisture, they turn into microscopic capsules of acid that destroy the metal from within. It is sulfur that makes modern steel so vulnerable. Roman iron, born in the flames of charcoal, was virtually sulfur-free. This gave it inherent immunity, a pure base to which the beneficial properties of phosphorus and slag were added. It was an environmentally friendly product, to use modern terminology. The metal absorbed the power of the tree, not the poison of the underground strata. The transition to coke was a necessary step. The planet simply did not have enough trees to satisfy our appetites. We got cheap steel that could be used to build ocean liners and skyscrapers, but we paid for it with the quality of every single kilogram of metal. We learned to combat sulfur by adding manganese and other additives, but this only treated the symptoms rather than eliminating the cause. Charcoal also provided a different reducing environment in the furnace. The process was slower and more delicate, allowing the correct crystal structure to form. It was slow cooking in the world of metallurgy, as opposed to the modern fast food of converters. The result was metal that felt different even under a blacksmith's hammer. Today, iron production using charcoal has survived only as an expensive hobby or for restoration work. The cost of such metal is dozens of times higher than that of ordinary steel. No one will build shopping centers out of it, but it was this gold standard of clean fuel that allowed the Romans to create things that have survived for millennia. We often forget that the chemistry of a material depends on what was put into it at the stage of its creation. Sulfur from coal has forever changed the DNA of our metal. We gained quantity but lost the soul of the material. Roman swords and nails were free from this original sin of industrialization. This difference in fuel is one of the main reasons why it is impossible to accurately reproduce the properties of Roman iron in a modern blast furnace. We would have to completely rebuild the technological chain. History teaches us that any transition to cheaper raw materials has hidden consequences that only become apparent centuries later. But clean fuel and the right chemistry would be useless without the hands of a master craftsman. Without someone to transform a shapeless sponge of metal into a reliable product. Guess how long it took to make this? While modern rolled metal comes off the mill in seconds, Roman nails were born from a long and exhausting dance between hammer and anvil. Roman iron was obtained in the form of bloom, a porous, spongy mass saturated with slag and voids. In this form, it was useless. To turn this semi-finished product into metal, it had to be forged hundreds, thousands of times. The blacksmith heated the bloom to white heat and began to methodically knock out the excess slag, compacting the structure. Each blow of the hammer was not just shaping, it was hardening by pressure. The metal was folded, flattened, folded again, and hammered again. This process resembled kneading puff pastry. With each cycle, the metal became denser, the pores closed, and the remaining slag threads stretched along the future product. This mechanical processing did what giant rolling mills do today, but on a much finer level. The blacksmith felt the metal, knew where the voids were, and struck precisely there. The metal grains were physically compacted. The surface layer of the product became particularly hard and smooth, as if polished by the blows. During the forging process, scale formed on the surface, which was also hammered into the top layer. This created an additional protective crust that was chemically resistant to environmental influences. Modern rolled metal has a loose surface layer that is exposed to the elements. Forged Roman iron was sealed by its own density. Hand forging also avoided the internal stresses that often tear modern metal apart. The metal cooled slowly, along with the furnace or in the air, undergoing natural tempering. It did not have the anger that arises from rapid cooling with water in modern conveyor production. It was calm and stable. The skill of Roman blacksmiths reached incredible heights. They could weld pieces of iron with different carbon contents, creating composite tools, a hard blade, and a soft, unbreakable base. And all this was done by eye, by the color of the heat, without pyrometers or computers. It was an intuitive knowledge of the material that is now almost lost. The labor costs for producing 1 kilogram of products were enormous. That is why every iron object was valued, cherished, repaired, and reforged. No one threw away a nail. It was straightened and used again. This attitude towards the material in itself prolonged the life of objects. Today, we try to imitate this process using powder metallurgy and special pressure treatment methods. But no machine can replace the sensitivity of the human hand, which adjusts the force of the blow depending on the response of the metal. Roman iron is not just a material, it is frozen human labor. We replaced the blacksmith with a machine operator, and the metal lost its individuality. Mass production has averaged out quality, making it acceptable but not outstanding. The Roman method was one of exceptional quality for every detail. But even the best blacksmith is powerless if he has poor ore. Did you know that the Romans mined iron in a completely different place than we do today? In the next chapter, you will learn about the blood of the earth that the ancients used. The Romans did not have geologists with sonar, but they had an amazing instinct for finding the right places. They mined a significant portion of their iron from so-called bog iron. These are reddish, iron-rich deposits that literally grew in swamps and at the bottom of lakes. This ore was poor compared to modern magnetites, but it had unique advantages. Swamp ore is a renewable resource formed by the activity of special bacteria. It is easily reduced at relatively low temperatures, which was ideal for blast furnaces. But the most important thing was its chemical composition. It was precisely in bog ores that the useful phosphorus and a number of other trace elements, such as vanadium or manganese, were often found in natural proportions. Ancient metallurgists empirically found deposits from which the metal obtained was good and durable. If the ore from a particular swamp produced rusty swords, the vein was simply abandoned. A brutal natural selection of raw material sources took place, stretching over centuries. Only those mines that produced quality ore survived. Today, we develop giant quarries by blowing up mountains. We take ore of any composition, relying on chemists at the factory to correct any defects with additives. We violate the nature of the material, forcing it to conform to a standard. The Romans, on the other hand, worked in collaboration with nature, choosing what was already almost ready for use. Roman logistics allowed them to deliver the best ores from distant provinces. The famous Norican iron from the Alpine regions was valued at its weight in gold for its natural alloying properties. Weapons made from this metal did not dull or rust. These were natural alloyed steels, the secret of which lay in the geology of a particular mountain. They also knew how to sort ore by hand, selecting pieces by color, weight, and texture. It was a painstaking enrichment process that guaranteed consistent results. Nowadays, giant flotation machines do this, but the master's eye was often more accurate. They literally knew every stone by sight. The use of local surface ores also meant that the metal in different parts of the empire was different. British nails differed from Syrian or Spanish ones, but the principle remained the same everywhere. The ore had to be alive, malleable to fire. Deep deposits, requiring hellish temperatures for smelting, remained untouched. Interestingly, many depleted Roman mines are now attracting the attention of geologists again. Analysis shows that the ancients chose precisely those veins where the content of harmful impurities was minimal. They mined the clean layer, leaving the dirty ore to us, their descendants. We often underestimate the influence of the raw materials on the final product. We think that technology is all-powerful, but Roman experience shows that if you want to bake good bread, you need good flour, not a bunch of chemical improvers. Swamp ore was that very organic flour for Roman iron. The secrets of ore selection died with the masters or were lost during conquest. But we see traces of this wisdom in every stainless artifact we pull out of the ground. It is a monument to the ability to choose the best that the planet has to offer. The Romans understood perfectly well that even their wonderful iron needed protection when constructing monumental buildings. They knew that metal, no matter how strong, corrodes over time when exposed to moisture and air. Therefore, when erecting large structures, they took special measures. The iron clamps used to fasten the marble blocks of the Colosseum or the Parthenon were not just connecting elements. They were part of a more complex system, thought out to the smallest detail. The Romans created a technology that allowed them to build virtually eternal structures. When Roman craftsmen inserted iron clamps into stone, they did not limit themselves to rough installation. They filled the joint with molten lead, creating a dense, well-fitting layer. This operation required precision and skill because the lead had to fill all the voids. After solidifying, it formed a flexible but protective shell. This protection prevented water penetration and metal corrosion. It was one of those hidden engineering secrets that gave Roman structures their incredible durability. Lead played several roles at once and was ideal for such tasks. It was soft and malleable, allowing it to fill any voids between iron and stone. It prevented water from accumulating in crevices where corrosion could begin. In addition, lead softened the vibrations caused by the footsteps of thousands of spectators or by minor earthquakes. Thanks to this, the iron did not experience sudden loads and did not deform. The soft metal served as a shock absorber, adding strength to the structure. This approach can be called an ingenious composite technology, in which rigid iron bore the main load and lead provided protection and durability. The Romans understood perfectly well that combining materials often gives better results than using a single substance. This idea was key to Roman engineering, and you can see it in a lot of their projects. They tried to combine materials in a way that let each one do its best job. That's why their buildings outlasted not just people, but whole eras. There were no random decisions in their designs. Unlike modern concrete, which has an alkaline environment and loses its protective properties over time, the lead shell remains stable. Concrete gradually carbonizes and ceases to protect the reinforcement, leading to corrosion. Lead, on the other hand, hardly reacts with water and air under normal conditions. It retains its structure even after centuries. Iron inside such a peculiar jacket feels almost like it is in a vacuum. This allows it to remain strong much longer than modern materials. This protective coating completely isolated the iron elements from the external environment. Even if there were areas of high humidity nearby, the lead remained a reliable barrier. It did not crack and did not allow water to reach the metal. This explains why many iron elements of Roman buildings have been preserved in excellent condition. Roman engineers essentially created a system that worked regardless of weather and climate. It remained effective even after 2,000 years. Roman architects knew that the combination of materials was of great importance. They understood that some types of stone could accelerate metal corrosion, while others, on the contrary, protected it. Therefore, they chose stones carefully, taking into account their chemical properties. Sometimes they used special gaskets or coatings of oil and resin to create an additional protective layer. This comprehensive approach allowed them to take every possible risk into account. All decisions were made with centuries in mind. This level of attention was not accidental. The Romans did not simply build buildings, but symbols of power and stability. Every element in these structures had to withstand the enormous pressure of time and nature. Therefore, engineers sought to anticipate future problems and solve them in advance. They used the knowledge accumulated by generations of craftsmen and enriched it with their own observations. This cultural continuity made Roman construction unique. It was based on time-tested practice. Today, we pour concrete over rebar and hope for the best because this method is simple and cheap. However, over time, moisture penetrates through the micropores of the concrete, reaching the iron inside. The metal begins to rust, increasing in volume and creating internal pressure. The concrete cracks and loses strength, leading to structural failure. We see this in the crumbling bridges and overpasses in various countries. Our buildings often age faster than Roman ones. Roman lead pouring technology physically prevented this scenario. The iron did not come into contact with moisture, which meant that corrosion did not start at all. Even if the outer part of the stone was destroyed, the internal structure remained stable. This gave Roman structures a huge advantage in terms of durability. Their buildings could survive wars, earthquakes, and human intervention. The technology worked regardless of operating conditions. Of course, this approach was expensive and required considerable effort. Tons of lead had to be melted and delivered to construction sites. Craftsmen filled each joint by hand, which took a lot of time. But the Romans considered these costs justified. They built for centuries and did not seek to save on the most important things. We can see the result today. Many ruins of Roman buildings still stand today, despite wars and natural disasters. The staples that looters did not pull out still hold the stone blocks in place. If the Romans had used methods similar to modern ones, the Colosseum would have fallen apart long ago. But thanks to their technologies, it survived the Middle Ages and lived to see our time. This is the best proof of the effectiveness of their approach. For them, durability was not a luxury, but a necessity. Interestingly, in the Middle Ages, many Roman buildings were destroyed not by themselves, but by people. Local residents dismantled the walls to get precious iron staples and lead. These materials were so valuable that they were reused 1,000 years later. Buildings became a kind of resource donor. People took everything that could be reused. This speaks to the high quality of Roman materials. Why did we stop making iron like this if it was so good? The answer is simple and cynical: money and speed. With the advent of blast furnaces and the Industrial Revolution, humanity chose quantity over quality. The bloomery method, which produced that very eternal iron, was incredibly slow and inefficient. Too little metal was obtained from a ton of ore, and too much coal and labor were required. The blast furnace made it possible to produce liquid cast iron in abundance. It was a revolution that fed the world with metal. Railways, machine tools, ships, weapons, all of this required millions of tons of steel. No blacksmiths with hammers could meet such demand. Quality gave way to quantity. We agreed that metal would rust, but it would be cheap and accessible to everyone. Along with technology, craftsmanship disappeared. The blacksmith, who felt the metal with his fingertips, was no longer needed. He was replaced by a metallurgist technologist who monitored the instruments. Knowledge of how to cook iron, how to select bog ore, how to feel the breath of the furnace became forgotten folklore. We replaced art with chemistry. The paradox is that modern science can explain why Roman iron was good, but the modern economy does not allow us to produce it. Making a batch of Roman nails today would cost a fortune. It would be a boutique product for millionaires. The market demands cheap reinforcement bars and disposable car bodies. We have created a culture of consumption where durability is the enemy of sales. If a car doesn't rot, you won't buy a new one. The Roman economy worked differently. It did not pursue endless growth and consumption. They needed things that would last for their grandchildren. We have also lost the locality of production. Roman iron was different in each province. It had terroir, like wine. Modern standard steel is the same everywhere, from China to the US. We have erased uniqueness in favor of standardization and GOSS. Attempts to revive old methods are hampered by a lack of raw materials, clean forests and bog ore, and a lack of skilled workers. It takes years of practice, not an academic course, to train a craftsman to the level of a Roman blacksmith. The chain of continuity has been broken. However, now that we are facing an environmental crisis and the problem of waste, we are beginning to think, maybe the disposable world was a mistake. Maybe it is worth bringing back some of the old approaches, albeit at a new technological level. We pay for cheap metal with the costs of repairs, environmental damage, and waste recycling. If we calculate the total cost of ownership, the Roman approach may not be so expensive after all. This story is a lesson that new does not always mean better. Sometimes, in order to move forward, we need to look back and understand what we have lost along the way. Today, scientists and enthusiasts are piecing together a picture of ancient metallurgy. Experimental smelting and reconstructed furnaces and analyses of museum exhibits are all attempts to recover lost knowledge. We don't just want to know how, we want to understand the philosophy behind that production. Roman iron is a reminder that humanity is capable of creating things that transcend time. It is a symbol of the union between man and nature, not their opposition. The nail from Inchill, the column in Delhi, the staples of the Colosseum, these are beacons of quality in an ocean of disposable plastic and rusting steel. We may never return to the mass production of wrought iron, but understanding the principles of its durability, slag fibers, phosphoric film, clean fuel, helps us create new materials. We learn from our ancestors using electron microscopes. We are beginning to appreciate dirty metal, realizing that purity is not always a guarantee of a material's health. We are rethinking the role of impurities and the structure of alloys. The Roman lesson is being learned slowly but surely. The history of Roman iron teaches us humility. With our computers and atomic reactors, we still cannot guarantee our structures the same lifespan that illiterate blacksmiths in sandals guaranteed. This gives us reason to think about where our technological vector is heading. Ultimately, iron is just earth that has temporarily taken shape through fire and human will. And how long it retains that shape depends on the respect with which it was treated during its creation. The Romans respected metal, and it repaid them with loyalty. We live in a world that is rusting away, but we have an example of a world that has remained strong. And choosing a path is not just a question of technology, it is a question of values. What is more important to us? Immediate gain or legacy? Those 7 tons of nails in Scotland, or a message in a bottle that reached its destination after 2,000 years? And the text of that message reads, "Do it well or don't do it at all." I hope this video has made you look at familiar things in a new way. We have examined the chemistry, physics, and history of one of the most amazing technological paradoxes. Now you know that the primitiveness of our ancestors is a myth, and that our progress has a downside. Roman iron stands as a silent rebuke to our consumerist civilization, reminding us that true quality is not afraid of time. What topic would you like us to explore in our next video? The secrets of Roman concrete, which becomes stronger in seawater, or perhaps the mysteries of Egyptian granite processing? Write your suggestions in the comments, and don't forget to subscribe to the channel so you don't miss out on new investigations into the technologies of the past.